before we jump into the derivatives of the inverse trig functions, let's just review some of this procedure, because I think this is worth going through. First of all, what is an inverse function? Okay. Well, before we can even get there, it turns out not all functions are invertible. We cannot undo all things. We know this. You break a vase, you can't undo it. Right? Same thing is true with functions. We can't undo all functions. So let's introduce some vocabulary here. A function f is said to be 1-to-1. Okay? I will often just write 1-1. Okay? I think other books do too, but maybe not. Okay? So a function will be 1-to-1 if whenever f of x1 equals f of x2, that means x1 must have equaled x2. Okay? That's the correct definition for a 1-to-1 function, but it's a little bit hard to understand the implications of that. Let's put that in other terms. In simpler terms, a function is 1-to-1 if different inputs always yield different outputs. Meaning different domain values always have different range values. Okay? That's an equivalent definition for 1-to-1. Okay? This is saying, hey, suppose two input values gave you the same output, then what must you know? You know that they must have been the same input values. Okay? All right. So which of the following functions are 1-to-1? Okay. Well, as a reminder, let's just put this off in the margins. This is not a 1-to-1 function right here. Why is this function not 1-to-1? Because, for instance, right here, I have three different, let's put that maybe with a different color. I have three different domain values, all of whom give that same range value. So that's not a 1-to-1 function. So graphically, it's very easy to identify non-1-to-1 functions. What we say is non-1-to-1 functions fail the horizontal line test. Okay? Meaning a horizontal line intersects the function in some places more than once. And sure enough, if I were to draw a horizontal line through part of this function, let's see, let's try this color here, through part of this function, I intersect the function more than once. So it's not 1-to-1. Okay. Careful, that has nothing to do with the vertical line test, which was the test to see whether a relation represented a function. Okay. Vertical line test was, are you a function? Horizontal line test is, are you a 1-to-1 function? Okay. Or are you 1-to-1? Okay, so which of the following functions are 1-to-1? Well, the first one is 1-to-1. Okay. Notice if you were to input a 2 into this function, it would spit out, well, let's see, if you were to put a 4 into this function, it spits out a 7. Is there any other number that will spit out a 7? No, there's not. If you set that equal to 7 and try to solve for x, you'll only get one solution for it. So it's a 1-to-1 function. Okay? How about this one? No, it's not a 1-to-1 function. Not 1-to-1. Okay? You could see that from its graph, right? The graph is a parabola, so it fails the horizontal line test, right? Or, notice, let's see, if you were to plug in a 3, it spits out -7. Let's say that. G of 3 equals -7. What's G of -3? It's also -7. What do we see here? Two different domain values gave the same range value, violating the definition of what it means to be 1-to-1. Okay? The log functions are 1-to-1. We'll talk about them more in just a moment. And what about the sine function? No, the sine function is not 1-to-1. In fact, it's about as un-1-to-1 as you can get, right? Because any range value corresponds to infinitely many different domain values. Okay? So it's not 1-to-1. That's particularly problematic for tonight's lecture, where we want to talk about the inverse trig function. Okay, put that on the back burner. All right. So now we know what a 1-to-1 function is. Okay. If you have a 1-to-1 function, then you can always do this procedure. Okay. If you have a 1-to-1 function, then we can define f inverse. Okay? Careful, this isn't f to the negative 1 power. I know I could understand you guessing that being f to the negative 1 power, but it's not. It's f inverse. Okay? F inverse. And we're going to define it this way. Suppose f of a is b. When you input an a value, it outputs a b value. Then you define the inverse to simply take and go the other way. When you input a b value into the inverse function, it outputs an a. Okay? So to practice that, let's create our own inverse function. Okay? But let's first say, we can always do this procedure. In fact, we can always do this procedure. But this procedure will always define a function, provided the original function is 1-to-1. That's why we need that vocabulary. We can always do this procedure if the original function is 1-to-1. Anyone know why that's true? Why do we need it to be 1-to-1? Why couldn't we just always say map it back to where it came from? Yeah, so let's say f of a is equal to c and f of b is equal to c. Then when I go to define the inverse, where should I send the inverse to? Both a and b? Well, then it's not a function, right? So that's why we needed it to be 1-to-1. Okay. So let's take this function right here, 2 to the x. Is that a 1-to-1 function? Put its graph in your head. Somebody should shake you up from depths of slumber. 2 to the x, what does it look like? Exponential function, right? It's 1-to-1. Okay. So it's a 1-to-1 function. Let's go ahead and evaluate some of the values. Let's see, f of 0 is 1. F of 1 is 2. Just for fun, let's practice some arrow notation. If I plug in a 2 into this function, what does it output? What's f of 2? 4. And if I input a 3 into this function, what does it output? 8. Okay, so I'm using some arrow notation here. You should just see that. So the first time you see it, it's not a shock. All right. Oh, here we said, is the above function 1-to-1? Is there any other number I could plug into 2 to the x and have it spit out a 2 other than 1? No, and that's true for all output values. So this is 1-to-1, yes. And what's the answer to the second question? Automatically. Yeah. Yes, those are the same question. Asking if it's 1-to-1 and asking if it has an inverse are the same question. Okay. I should be a little more careful here. Does it have an inverse? Let's add in the word function. You can always invert something, but it won't always be a function. That's what we were just talking about. Okay. So let's work with this inverse function. What should be f inverse of 1? F inverse of 1 should be 0. And what should be f inverse of 2? It should spit out a 1. Since when I plugged a 1 into the original function, let's look at that. I plugged in a 1, and it spat out a 2. So when I plug in a 2 into the inverse function, it needs to spit out a 1. That is the domain range flip-flop of a function and its inverse. Okay. Using the arrow notation, when we input a 4 into the inverse function, what should it spit out? A 2. And when we input an 8 into the inverse function, it should spit out a 3. Okay. What is f inverse of x then? What function did we just define there? What function that when you plug in an 8, it spits out a 3? When you plug in a 4, it spits out a 2. And always when you plug in a 1, it spits out a 0. What function is that?
Log base 2.
Yeah, the log base 2 of x. Any college algebra book, before it can introduce logarithms, has to spend a section on talking about inverse functions. Because you can't talk about logarithms without using inverse functions. You shouldn't. Okay? All right. Okay, so let's go ahead and sketch the graphs of these two functions. So let's see here. Here we've got the graph of 2 to the x. And here we've got the graph of log base 2 of x. Notice the domain range flip-flop. What is the range of red? The range. What's the range of red? 0 to infinity. What is the domain of green? What's the domain of green? 0 to infinity. What was the domain of red? Minus infinity to infinity. What is the range of green? Minus infinity to infinity. Okay? All right. There's a couple points. If you wanted to put some points on here, that might be helpful. Here's the order pair 0, 1. That's the same as the order pair 1, 0. Folks, logarithms aren't a mystery to me because I always think of them in context of their exponentials. There's one other fact here, and that's not unique to this picture that we just drew. For all functions and their inverses, if they're 1 to 1, and notice you see they are, for all functions with their inverses, we see that they're symmetric about the line y equals x. That's related to the fact that if you take the log base 3 of a number and then raise that exponentiated over 2, you're back to the number you started with. When you compose a function with its inverse, you just get x. Another way. All right.